Ever had that brilliant idea? The one you were sure was going to be a game changer. You spend weeks, maybe months coding it up, running tests, and then, well, nothing. It just doesn't deliver.
Oh, absolutely. That's almost a rite of passage in AI research, isn't it? It happens constantly.
Right. And the traditional wisdom has always said, look, if you want to know if what idea works, you just have to build it, test it empirically.
Which means a serious commitment. We're talking researcher, time, effort, huge amounts of compute sometimes. It all adds up.
Exactly. And that empirical process, well, it's necessary, but it really slows things down. It's a bottleneck.
A huge bottleneck. Every path you explore needs those resources. And if the idea fizzles out, that's basically wasted investment. It's a fundamental hurdle in the field.
It feels like a high stakes gamble every time. So it makes you wonder, what if? What if you could somehow figure out which ideas are likely winners before doing all that heavy lifting?
Uh-huh. Improve the odds significantly.
Yeah. Could large language models, LMs, could they actually develop that kind of predictive insight, that sort of research intuition?
Well, that's exactly the question behind this really fascinating new study we're looking at today. It's from researchers at UC Berkeley, Stanford, NYU, and George Washington University.
Okay.
We're diving into this paper by Wen and colleagues, and they tackle this, well, this almost futuristic idea directly.
So our mission for this deep dive is really to get into the weeds of their academic approach. What were the key innovations here? What makes their setup, their system, and honestly, their results stand out, especially when thinking about predicting where AI research is headed?
Well, the problem they start with is pretty stark. Like we said, empirical AI research is fundamentally capped by the sheer cost and effort of building and testing things.
Right. You need skilled people writing code, setting up experiments, tweaking parameters, analyzing everything.
And you often need serious computing power. So every idea that doesn't pan out, that's time and compute down the drain. On a big scale sometimes.
It's like planning, I don't know, dozens of expeditions hoping to find treasure, but you have no map, no real clue which ones might actually pay off. You desperately want a better map, maybe a crystal ball.
Exactly. Or at least something that gives you better odds. The goal is smarter prioritization. If you could reliably say, okay, these ideas seem more promising, you could focus your efforts there first.
Which would speed things up considerably.
Dramatically. Boost efficiency across the board. But like you asked earlier, how on earth do you predict an experimental outcome without running the experiment? It sounds almost impossible.
It does feel a bit paradoxical, right? How would an LM even begin to know?
So that brings us to their core hypothesis. Think about how human researchers develop intuition. It's through years and years of experience, right? Reading tons of papers, trying their own ideas, seeing what works, what fails, in what context.
Okay, learning from patterns over time.
Precisely. And they theorize that LMs, having ingested just massive amounts of text, including probably a huge chunk of the scientific literature, might be able to sort of distill that same kind of intuition, maybe even more effectively than a single human could.
Okay, let's unpack that. Because predicting future experimental results just from an idea's description, that sounds incredibly challenging. How do you even set up a proper academic test for that? You need a way to score the LM, right? A ground truth.
Yeah, and this is where their first really big innovation comes in. There just wasn't any benchmark for this specific task. Nothing existed. So step one, they had to build it from the ground up.
Wow. Okay, that's a major piece of work in itself. So how did they structure the task for the LM? What does it actually do?
They framed it as a pairwise evaluation. So the LM gets presented with detailed descriptions of two different research ideas. Crucially, both ideas are aimed at solving the same problem.
Like two different approaches to make a neural network faster, or two new ways to augment image data.
Exactly. And the LM's job is simple: predict which of those two ideas will perform better when actually tested based on the results reported later in the paper they came from.
Okay, why pairs? Why not just judge one idea on its own? Like, will this work?
Well, will it work? It's kind of vague, isn't it? Success is often relative. It depends on the benchmark, the data set, what you compare it to.
Right.
Comparing two ideas head to head gives you a much cleaner, more objective signal. The ground truth becomes really concrete. Idea A beat idea B on these specific metrics in this specific paper or the other way around.
Ah, so you get a clear binary label, A wins or B wins, based directly on the paper's reported empirical results. Makes it objective, measurable.
Precisely, an objective task with verifiable ground truth.
Got it. But okay, collecting thousands of these pairs, digging them out of research papers while making sure you don't accidentally give the LM the answer, that sounds tricky. How did they manage the data collection rigorously?
They built an automated pipeline. Actually, they used advanced LMs like Clob 3.5 Sonnet to help with this. It scraped info from thousands of papers from conferences and MLP, machine learning, computer vision, and robotics.
What exactly did it pull out?
It extracted the research goal, the names or labels for the different ideas being proposed in the paper, and really detailed summaries of how each idea worked, its methodology.
And the crucial part.
The crucial part, the LMs doing the summarizing were explicitly told not to mention any empirical results from the paper. Zero leakage of the actual outcomes.
So the test LM only sees the what and the how of the idea, not the did it actually work part from that source paper. That's a critical control.
Absolutely essential. Then, for creating the pairs, another control, they only compared ideas that came from the same paper.
Why is that important?
Because if you compare ideas from different papers, you introduce all sorts of confounding factors, right? Different data sets, maybe different hyperparameter tuning, different evaluation details, even slightly different goals sometimes. Sticking within the same paper minimizes those variables. It isolates the comparison to just the ideas themselves as much as possible.
Okay, that makes sense. Controls for the experimental environment. And how do they decide the winner if a paper reports results on multiple benchmarks?
Good question. They look at all the relevant benchmarks reported for those two ideas in that paper. Idea A was declared the winner if it performed better than Idea B on the majority of those benchmarks. They filtered out cases where it was a tie or the comparison wasn't clear.
Okay, majority vote across metrics. Now, the train test split. How did they ensure the test set really forced the LM to predict future outcomes? Things it couldn't have possibly seen during its own training.
Right, this was super important for testing true generalization. They used the knowledge cutoff date of the LM they were fine-tuning, which was GPT 4.1. That cutoff was around June 1st, 2024.
Okay.
So the test set only included pairs where at least one of the two ideas was first published after that June 1st date.
So the base GPT 4.1 model literally had no chance of having seen those specific post-June ideas or their results during its massive pre-training phase.
Exactly. Guaranteed novelty for the test set. And they built up a pretty sizable data set this way, 6,000 pairs for training the system, and then 1,585 pairs for testing on these future ideas.
That sounds like a solid foundation for a new benchmark. But using an automated pipeline, even with advanced LMs, to parse complex research papers, I imagine mistakes can happen. Did they worry about the quality of the automatically extracted data, especially the ground truth labels for the test set?
They absolutely did, and they addressed it with a really thorough human verification process, especially for that critical test set.
Okay, what did that involve?
They got 16 experienced computer science and electrical engineering students, people familiar with reading these kinds of papers, and had them manually check the automatically generated test examples. And not just once, they did this over 4 iterative rounds of verification and correction.
4 rounds. Wow, that is meticulous. What kinds of errors were they catching?
It shows the academic rigor they aimed for. Yeah, they were fixing things like incorrect win condition. Maybe the automated system got confused about whether higher or lower was better for a specific metric, like perplexity.
Oh, right. Lower is better for perplexity. Easy mistake for an automated system.
Exactly. Or incorrect empirical results. Maybe the extracting LM hallucinated a number or just misread a table. This whole intensive human in the loop process slashed the estimated error rate in the test labels way down from about 11% initially to just 2.5%.
That's a huge improvement. So that human oversight was key to trusting the benchmark's ground truth.
Definitely crucial.
Okay, so they've built this robust, verified benchmark. Now, the really exciting part, how do they actually build the system to make the predictions? It gets the idea descriptions, it has historical context up to June 2024, but it can't see the future results. What's the system architecture look like?
So their system essentially has two core components working together. First, a powerful base LM specifically. They used GPT 4.1, which they then fine-tuned. And second, an agentic paper retrieval module.
Okay, let's break that down. The retrieval module first. What does agentic mean here and what's its job?
Think of it as an automated research assistant that helps the main LM. Agentic means it's not just doing a single simple search, it's more iterative. It uses retrieval augmented generation, or RAG.
RAG, right, we hear that a lot.
Yeah, so it takes the input idea descriptions, generates search queries from them, then uses a neural search tool. They use something called AI to find relevant published papers. But then it goes further. It summarizes these papers, checks if they're actually relevant, maybe refines its search based on what it finds. It's a multi-step process.
And its goal is to give the main LM background info, like related work.
Exactly. Just like a human researcher would read up on existing literature before evaluating a new idea, it provides context.
But wait, how do they stop this module from leaking future information since it's retrieving papers?
Ah, another critical control point. The retrieval module also adhered to the June 1st, 2024 cutoff date. It only retrieved and considered papers published before that date.
Got it. So pulling historical context, foundational work, similar ideas in other areas maybe, but absolutely nothing about the actual test papers themselves.
Correct. Purely historical context from the literature available before the knowledge cutoff.
And you mentioned summarizing retrieved papers. Did they find anything interesting about how it summarized them? Like just using the abstract versus something more?
Yes, this was actually a really key finding. They found that summarizing the entire content of the relevant retrieved papers instead of just relying on their abstracts made a huge difference.
How huge?
It substantially boosted accuracy in their preliminary tests. Just changing from abstract-only summaries to full paper summaries jumped the accuracy from around 38.8% up to 53.0%.
Wow. Okay, that's a massive jump just from summarizing the whole paper. Why do you think that is? What's in the full paper that's so much more helpful than the abstract?
Well, abstracts are designed to be short, right? They hit the highlights, the main claims, maybe the novelty. They often lack the deep methodological details, the ablation studies, the discussions of limitations, the nuances of the experimental setup.
Right, all the stuff you actually need to understand how something was done and why it might have worked or failed.
Exactly. Relying only on abstracts might make the model latch onto superficial similarities or maybe bias it towards older, very famous papers whose abstracts are well known. The full paper provides much richer, denser information about the nuts and bolts of related research. Even if it's not the exact same idea, it gives the LM a much deeper understanding to draw upon for its prediction.
That makes a lot of sense. Richer context leads to better predictions. Okay, so we have this RAG system feeding rich historical context from full papers published before the cutoff. What about the other piece, the fine-tuned GPT 4.1?
So that base GPT 4.1 model was then trained, fine-tuned on those 6,000 historical idea pairs from their training set.
Okay,
This training process specifically taught the model how to take the two idea descriptions, plus all the relevant historical context provided by the RGEG system, and make that final prediction. Which idea is likely to perform better? It's about coaxing out and sharpening that specific predictive skill.
eliciting that capability, as they say. So how did this whole system perform when they unleashed it on the test set? Those 1,585 pairs of future ideas published after June 1st.
The results were really telling. First off, they tested baseline LMs, like GPT 4.1, in a zero-shot setting, just giving it the task instructions and the data, maybe with the RAG context, but without the specific fine-tuning.
Yeah,
Performance was basically random chance, around 51.9% accuracy, which is important. It shows that these powerful models don't just naturally have this research prediction ability built in from their general pre-training.
right. They aren't magically good at this specific nuanced task.
Exactly. But then came the fine-tuning effect, training GPT 4.1 on those 6,000 historical examples. That caused a massive jump. Accuracy went from that near chance 51.9% all the way up to 77% on predicting the outcomes for these genuinely future ideas.
Wow. 77% accuracy on predicting winners between ideas published after its knowledge cutoff, just based on the description and historical context. That really shows this capability can be learned or elicited with the right training data.
Precisely. It's a clear demonstration. Interestingly, they also tried using chain of thought prompting during fine-tuning, where the model explains its reasoning steps.
Did that help?
Not really in this case. It didn't improve the results. Their thinking was that maybe if the base model is already performing poorly on a task, its self-generated reasoning just isn't high quality enough to provide a good training